Hello, everyone. Welcome to our third hot topic session. This afternoon's subject is gradual versus rapid change in the Sahara. My name is Carrie Morrill, and I'm the convener. We have two invited speakers for this session, Brahim Damnati from Morocco and Jingyu Liu from the University of Wisconsin-Madison. Unfortunately, Professor Damnati is not able to join us this week. He had an emergency and wasn't able to make the trip to Corvallis. So I will try to step in and give a brief overview, mostly on the proxy records, and this will take about 15 minutes, and then I will turn the stage over to Liu, who will be talking about some model results. So as I said, the topic of this hot topic session is gradual versus rapid change in the Sahara, and we're looking at the transition from the early to mid-Holocene to the late Holocene. So from the green Sahara, or the very humid, moist state of the early mid-Holocene, to the later dry state of the Sahara today. And this map shows the distribution of vegetation for today and during the early to mid-Holocene 6,000 years ago. And this is all, the 6,000 year ago slide is based on pollen data. So today, of course, there's desert vegetation or lack of vegetation and desert environment across much of the Sahara. And then into the Sahel, you get some amount of steppe and savanna. But the situation was much, much different in the early to mid-Holocene, where the steppe and savanna vegetation expanded across much of the Saharan desert. And also to point out another important part of the environment that was different, there were several very large early to mid-Holocene megalakes in the Saharan desert. Probably the most famous being the Lake Mega Chad, which is just a larger, much larger version of today's Lake Chad. Lake Mega Chad was about the size of the area of Belgium. And there are many other megalakes in the northern part of the Sahara, which today have totally gone away and are just deflated lake basins. Now, the main reason for the humid period in Africa in the early mid-Holocene relates to changes in insolation. Shown here. This is a June, July, August insolation at 20 degrees north. And of course, in the early to mid-Holocene, insolation was at a maximum. And this caused the monsoonal circulation in Africa to intensify, and the position of the ITCZ, its northward position as it sweeps back and forth seasonally across Africa, its northward position is thought to have moved further north, wettening the Sahara and allowing increased vegetation in large lakes. But of course, you can see that the insolation changes very smoothly through time to the late Holocene. And there's a big question as to whether the monsoon circulation and the vegetation in lake basins in the Sahara also changed smoothly. Or on the other hand, they could have changed much more rapidly in a series of, or maybe just one step function. And so this kind of frames the debate of this hot topic session, which was the end of the African humid period abrupt? And I'm going to review some of the proxy evidence, and I'm going to focus on just a couple of the best known records. And the main conclusion here is that some proxies say yes, that the end of the humid period was abrupt, but others it's a little less clear, and it looks much more like a gradual transition. And just to summarize, I'll be talking about a dust record, Peter Domenical's record from off the western coast of Africa. And it looks like a clear, very abrupt signal. Then I'll be talking also about a pollen record, where it looks much more like a gradual transition from the early mid-Holocene to the late Holocene. And I'll finish up presenting some of Professor Damnati's lake record results, his lake status database, where there's perhaps some indication of abrupt shifts, but also some gradual trends as well. So this is the very famous dust record published by Peter Domenical and others in Science from ODP Site 658, which is a great place to look for dust coming right off the continent of Africa to the east. And they measured terrigenous material or dust in this core. This scale is backwards from the earliest time period here, going forward through time. And this orange line represents the insolation, and it's actually been flipped such that this is lower insolation in the late Holocene and greater insulation in the early Holocene. And the percent terrigenous material in this core shows a very clear step change about 5,700 years ago. Now, one potential issue with this record is that they're measuring percent terrigenous material, which is a residual from the measurements of carbonate and opal in the core. So because all of these three components must sum to 100%, then there's some potential for effects of dilution, or if one of the other components is changing in strength, then this could be driving the terrigenous signal. So they did a little extra work published by Adkins et al. In Paleoceanography in 2006, where they were measuring the actual terrigenous flux. And this was measured based on thorium isotopes. And the blue line here is the curve that I just showed, and the red line on top is the terrigenous flux. And you can see it has much the same shape with this very abrupt step change from at the end of the African humid period, lasting on the order of a century or so. Now, to look at a completely different record that gives a very different story of this transition, go to Lake Yoa, which is in northern Chad, and this was a record published by Stefan Kropelin and others in Science last year. And this it's a very unusual lake. One of the problems with finding paleo records of the transition of the mid-Holocene transition in Africa is that many of these lake basins, which are a primary source of information, dried up, which exposed the lake sediments, allowed them to be deflated and eroded and sort of truncated the sections. So it's very hard to actually get a good sense of the timing of the transition and also its speed. But this is an unusual record because it comes from a lake that still exists. It's one of the few lakes in this region that is still in existence. And this shows right here the position of the lake in relation to the ITCZ today. Now this is, they measured many different things. I'm going to be focusing mostly on their pollen results and then a little bit on the surface water conductivity inferred from chironomids and from diatoms. And their overall conclusion is that they see a very continuous succession of vegetation through the mid to late Holocene, and no real evidence for abrupt shifts in vegetation or in lake status. First, they see a decrease in tropical trees here at about between 5,000 and 6,000 years ago, which is followed by a very short-lived increase in Sahelian vegetation, followed by a longer millennial scale increase in semi-desert plants, then followed by an increase in Saharan plant taxa. So it's this idea of shifts in plant types all the way through the transition, where there's no sudden decrease in plant or vegetation. Now, this record up here, the surface water conductivity, actually does look like it could show an abrupt shift in the lake from very freshwater conditions to saltier conditions. But these authors argue that this wasn't an abrupt change at all, that it was a site-specific threshold as this lake moved from an open lake with an outflow to a closed lake, in which the only loss of water from this lake was from evaporation. So that this was not necessarily caused by an abrupt change in precipitation or evaporation. It just happened that this was the time at which this lake transitioned from being an open lake to a closed lake. So a very different situation than what we see from the Dominical dust record, raising questions about how can you see an increase in dust if perhaps vegetation and lakes, the two potential things that are affecting dust creation, only changed very gradually through the Holocene. So I have a couple of slides from Professor Damnati and his recent research related to the lake status database of North Africa. And what he's been working on is an update of the original African lake status database. And the original database was completed about 2 decades ago and included information from 146 basins. But there have been much new data published since then, and he is extending the compilation. So for changes in lake status, he's looking at several different ways of reconstruction. One is stratigraphic data, looking at lithology of sediments or grain size, which give a lot of information about the lake depth. Geochemical data, such as stable isotopes or conductivity inferences, which give a lot of information about the hydrologic budget of the lake, the evaporation and precipitation ratio. And he's also using paleoecological data, such as diatoms, ostracods, and mollusks, that give indication about depth or salinity tolerances. And he's using archaeological data. And his reconstructed lake status histories are based on the consensus interpretation of all these available lines of evidence. He's following the status coding, the coding conventions that are in the global lake status database, which have 3 different categories. One for the lowest lake status, 2 is intermediate, and the 3rd is high. And these are all based on quartiles. And the high class corresponds to the upper quartile, which is the highest 25% of that lake's variation in depth or level during the entire period of record. And he was doing this to ensure compatibility with the available global data set. So I have 2 maps of what some of these time slices look like. This is a map of the difference in lake status from 9,000 radiocarbon years BP to present. And that would correspond to about 10.2 calendar Ka. So this gives an indication of the range of the lake sites, which cover a large part of North Africa. And it also just gives a sense of how they all show wet or very wet conditions. So they agree with each other very well. And this is just another example of a map for the difference between 6,000 radiocarbon years ago and present. So he has data on 500-year intervals, time slices such as that, and this is the compilation of all of those time slices for the last 21,000 years. And along here is radiocarbon years, so we have 0 to 18. And the darkest is the highest lake status, and the medium gray is the intermediate lake status, and the lightest gray is low lake status. And along here is the percent of lake basins that fall into each of those categories. Now there is some evidence, he pointed out 2 things to keep in mind. One is this abrupt increase in lake status or lake depth at the beginning of the Holocene. And another is this gradual trend towards decreased lake status, but with some jumps in it here. And there's one kind of maybe more particularly around about 5 radiocarbon BP, which is equivalent to about 5.7 calendar Ka. So I will leave you with his acknowledgments, and I can take any questions that people have. I can try to answer them to the best of my ability, or just turn the stage over to Lou. So does anyone have any questions? Okay, then.